I'll be talking about our paper on continual learning for effective robotics and taking you through why it is needed, what does it mean, and how do we achieve it. Let's get started. Effective robots are becoming ubiquitous in our lives. We see them involved in healthcare programs, servicing us in restaurants, assisting the elderly in care homes, and slowly becoming our everyday companions. The widespread application of these robots demand that they're equipped with abilities to perceive users, their effective behavior and responses, and also learn how to interact with them. Starting with the perception model right out of the box, they must learn to interact and adapt with users during interactions, extend and apply this learning with other users, and then adapt to different user groups as well. This process of learning and adapting continues as the robot interacts with more and more users. So what is the problem with traditional approaches to learning? Well, robot capabilities are a result of models trained and fine-tuned in isolation on large benchmark datasets. This training, however, can be vastly different to real-world interaction settings and require robots to follow a cumbersome and costly process of relearning and adaptation. Continual learning, on the other hand, enables incremental integration of knowledge with sequentially made available data. These models are highly sensitive to data conditions, adapting with new information without forgetting the old. A continual learning algorithm adapts the current model using the newly acquired data about a task along with the past experience, updating both the model and the experience in the process. Let's consider a concrete example of personalized affect perception. In this setting, the robot is trying to perceive and understand the effective behavior of this user in home context, trying to engage them. Most traditional affect perception approaches are insensitive to contextual attributes and use a pre-trained perception mechanism that does not adapt. They ignore specific nuances in users' behavior and try to fit all users under one generic perception model. Continual learning, however, uses a pre-trained model only as a starting point but evolves with each user. Interactions with the users help gather more data, and the robot updates its model with each interaction, personalizing towards each user. Another example is the case of learning context-specific behaviors. Here, the robot is trying to learn to interact with and care for an elderly lady, reminding them to take their medicines. Although traditional reinforcement learning might also be able to learn such high-level tasks, they would require large amounts of interaction data and huge computational resources, yet learning very specific behaviors. Further, as human interactions are fluid and switch contexts frequently, this learning is even harder and may become intractable in real time. Interactive reinforcement learning does, however, provide a solution where humans become a part of the learning process of the robot. For the continual learning case, we propose to use such interactions to provide feedback to the robot. The robot might also acquire user-specific and task-specific contextual attributes, helping it improve its behavior with each ongoing interaction and with each user that it interacts. An effective robot, thus, would need to learn how to perceive user behavior, acquiring new instances of data for each interaction, while also learning to interact with the users. And this becomes multifold in real-world situations, where a robot not only needs to acquire new instances of learning for each user or a task, but also need to learn how to apply this understanding across subjects, learning new conceptual mappings. The continual learning paradigm is well suited for such learning, and effective robots would benefit from such learning methodologies. So all this sounds great. What is the problem, you might ask? Well, there are many challenges that need to be addressed for this to become a reality. Let's discuss some of them and see how we can attempt to address them. Firstly, person-specific data is limited and hard to acquire. As interactions are the only source of data, the robot might perform poorly during initial interactions, harming the user's experience. To address this, one solution could be to hold introductory rounds of interactions whenever the robot encounters a new task or a user. This will enable the robot to collect more data and update its learning before even starting a task. Yet, this data might also be limited and insufficient. Thus, generative models can also be applied to simulate additional data to augment learning. The other issue is obtaining ground truth evaluations. This is an issue particularly for affect perception, as human affect is subjective and ground truth varies between users and contexts. Unsupervised learning is usually applied to get around this problem, but in real-time interactions, this might also become intractable. We suggest to focus on learning normative baselines by holding initial interactions in context-neutral settings. This will help establish a norm for the user behavior, and deviations from such norms can be easily detected using continual learning approaches. Additionally, Grouping the users together using contextual attributes of personality or gender can help speed up learning initially and then can be later fine-tuned during interactions. Another problem in real-world interactions is that human interactions are fluid and move back and forth between contexts. Further, these contexts might overlap and the robot would have a tough time keeping up with the changing environments. To remedy this, continual learning models can be made context-aware by learning context-specific embeddings separately and using them as an additional input to the model. This would allow for a smarter context switching for the robot, facilitating interactions with humans. Another major issue for the robot is limited hardware capabilities they possess. The robot needs to balance memory with computation, both of which are essential for learning. Continual learning algorithms allow for slow forgetting in the models, where unimportant information is slowly forgotten, making way for new knowledge. Additionally, generative models can also be used to make robots more memory efficient, as well as apply cloud-based solutions that offer different robot functionalities as services, reducing the load on the robot. Finally, even if we are able to address all these challenges, an important concern for effective robots is to address the issue of fairness and reproducibility. Here, reporting continual learning metrics such as forward or backward transfer of information might help establish how the robot applies learning from one user to the other and how much of the user information is forgotten over time. Additionally, traditional metrics such as F1 scores and ROC statistics help establish QA standards for the robot performance. In the end, to sum up, we established that real-world interactions are complex and unpredictable and requiring effective robots to integrate new information on the fly. In particular, we discussed personalized affect perception and behavior learning as two concrete examples that stand to benefit from continual learning models the most, enabling lifelong evolution of robot capabilities. Here, I would like to thank my co-authors for their contribution as well as our sponsors. Thank you all very much for listening.